So a t-test for dependent means will have a null distribution that is t. The null distribution that we have seen so far is a standard norm. But here, the null distribution is t. I mentioned a while ago that depending on the test, the null distribution will change. But it is the job of people like me to tell you what the null distribution is. I am giving you that the null distribution here is t. T requires something called df. Do we remember what df is? Elizabeth? Right?
Degrees of freedom.
Degrees of freedom. And for this case, it is always n minus 1. If you have to take a guess as to what n is, what is n? Some books refer to sample size using lowercase n, but your book uses uppercase n. In the previous start course, you would have looked at a t-test. That is for independent means, or it's simply forming mu with unknown variance or standard deviation. That's the scenario you encountered last time. I'll explain this, then we can go to that one. So we have one population. Let's say the population here, college students. Good. And I'm going to make a research hypothesis. I'm sure a good many of you here like Chick-fil-A. The line there, especially. No alternative. Mu is the average amount spent on lunch by college students at Chick-fil-A. So, we want to make some sort of research hypothesis for a population. Am I talking about a population? Yes or no? Yes, I'm talking about college students. What am I interested in specifically about college students in this problem? That and more specific is about how much they spend on lunch, maths and
It was the
same thing. So I am referring to the population, which in this case is college students. And specifically, what am I interested in? The average amount that I spend on lunch by college students at Chick-fil-A. Good. Now, one of you can make a research hypothesis. Who wants to do it? Did you hear what makes are we talking about week or month? We can say that you like Chick-fil-A.
No, I actually can't eat there.
Oh. Okay, let's do meal. That's easy. Like $12. Okay, $12 what? You know, we have to frame it of the concept.
$12 or more.
So
Maybe the research.
greater than 12 bucks, right? So we can either do greater, less, or not equal to. So those are the three types. So Riley is going for greater than 12. Good. The opposite would be the to verify, we randomly select a sample. Of course, the sample has to come from the sample of college students. We do not know what the population mean is. No one knows. We frame a hypothesis. In order to verify the hypothesis, we need a sample. So I collect a random sample, bunch of numbers. If I have a bunch of numbers, can I find their mean? Average? Yes, add them all, divide by, and use your calculator. Do we remember the standard notation for mean? Mu would be for population. So the one that you get from the sample. X bar, right?
That's just like.
X bar. Okay. That is the sample mean. S would be the sample standard deviation. Okay. When I get to this part, I'm going to change the formula. I'll write this as for this. What the notation your book uses. The book refers to sample mean as uppercase M. I want to use uppercase M because to me it refers to mean. But we'll cross that bridge when we get to it. So we have sample mean, and then we also need sample standard deviation, which is going to measure the amount of variability that you have. We will always encounter variability because we're dealing with random stuff. Bunch of college students, things are random. That's the question. Suppose I collected a sample of size n equals 64. Hypothetically. Good. And hypothetically, I get a mean of 11.20. Good. Do I need a statistical test if the sample mean ended up being 11.20? A test of that kind. Which is one-sided, right here. Yes or no?
You said there's no variance, or we don't have the variance.
We don't have the variance.
So yeah, I would think you
Do need it, is what you're saying, okay?
Is it because it's not greater than 12?
So yes or no, Scott? So, Okay.
Well, aren't you trying to prove the alternative?
We're not proving, we're just trying to see if there is evidence to support. Never use the word prove, because it could be wrong, right? It's not a deterministic thing. We are trying to see if there is evidence to support this. And think about the purpose of a hypothesis test. I'll give you a hint. There is effect. What game? $11 letters, starts with S, ends with T. Where's the sound coming from? Raleigh, was that you?
No.
It wasn't you?
I don't
Or it's not
I don't think it's significant.
significant. So there is the concept of finding an effect and finding a significant effect. So when would we assess significant effect? Well, I'm trying to see if that average is greater than 12. So in order to have an effect, I need to have a number bigger than 12. Do you agree? Because that is what I'm testing for. So I've got to start with something that is bigger than 12. If it is bigger than 12, then I will decide using a test to determine or decide if it is significant or not. Agreed? Did I start with an effect to begin with? No. So I don't need a test because that number is less than 12. So if I change to 12.50 or $12.50, the answer is yes. Why? $12.50 is bigger than 12. We have an effect, but we want to address if the effect that we observed is significant or not. Think about the curves that we drew last time. One had little overlap, tiny effect size. The other, large overlap. Today, we use that curve. So it is the effect that we are looking for. If there is no effect at all, or if it goes to the other side, no need for the test. Here, we need a test. Because I have 12.50, but as Riley pointed out earlier, that $12.50 average will be affected by sample standard deviation. Little variability, too much variability. It could also be affected by sample size, tiny sample, really large sample. So several factors come into play when we have something that concludes that we have an effect. We want to determine if that effect that we observe is significant or not. Good. And that's why the test comes to play. So this entire thing to test for just mean wants to test about a mean being greater than something, less than something, not equal to something. And you picked an example of greater than. We have only one population, and I didn't know the variance. I used the sample deviation variance. Do we follow this scenario? Okay. Opted outside. We write this. There are a couple of types. First one called repeated measures. What I'm trying to do now is to cite the differences between a regular t-test and over there, dependent means t-test. I went over this, maybe the first week of classes or the second week of classes. You can take a statistical procedure and apply to any type of data point. But if you violate assumptions, if you use the wrong test, you are lying to people. Yes? So you've got to be careful on which test to use. So people like to call this as repeated measures design. The other case, break and paste design. So repeated measures, pre-post design. I'll start with pre and post, easy to follow, then we can get to pre-post. Remember that anxiety drug problem that we did. And I know that was whether the drug is effective, drug is not effective, and the alternative drug is effective. So let's say we ask patients to rate anxiety level 0 to 10 before treatment. Good. I want to see the effect or test the effect of the drug. So that would be my intervention. In our case, the anxiety drug. Let me ask you, what should we measure after the intervention? Okay, we're going to measure the same anxiety level, same levels with the same scale, 0 to 10. 0 means no anxiety, 10 freaking out, big time, panic attacks. Good. Before is the pre part. After is the post part. Let's say I looked at 16 people, randomly selected. When you do the intervention and come over here, would you ask the same 16 people or a different set of 16 people? Has to be the same. If you went and asked a different set of 16 people, you are lying. Yes, has to be the same set. So, same 16 participants. I have 16 of them. So I can't just pick one of their ratings and come to a conclusion. Do you agree? If 16 people responded, I can't pick one that I like and throw the rest away. So what is a good measure that accounts for all 16 of them?
Same for me.
The average. So I need an average rating. So we're going to make use of that average to determine if there is a change or not. So clearly, we're going to assess average anxiety level. We call it dependent because the average anxiety level I recorded before treatment, the average anxiety level that I recorded after treatment, they are connected. Do you agree? Same participants, the only thing that happened is the intervention. Hence the name dependent means. Good. So if you have a scenario of this kind, we cannot use that. You need this one. All right. Okay. What about the repeated measures? Repeated measures occur usually in scientific settings. We know what the word measure is. Some measurement. Repeat things you're doing over and over. So consider you have an experiment. You're doing the first trial. And then you're doing one more trial. It is the same experiment. Yes. You're just repeating it one more time. Sure, I can repeat it 10 more times, nothing more. If it is a good experiment, trial 1 and trial 2 must get consistent results. Do you agree? If it is an awful experiment, huge difference between the two. And a person, the experimenting person, cannot rely on an experiment where one trial is giving a result that is way different from another trial. Garbage experiment. So we want consistency here. So repeat, measure, that is repeated measures. Occurs in biology, pretty much a lot of sciences that involve experiments. We want to see consistency. Good?
They're kind of both opposites. Like A, you want consistency, B, if you get consistency, it's like not.
Good catch. So here, a valid hypothesis that we're testing for is for the difference to be 0. They have to be consistent. In other words, they have to be really close to each other. Yes? There, I want one to be way far away from the other. Then I will know that there is an effect. I used the word already, but let me ask again, or let me ask you, how do we know one, or how do we know the drug is effective? Would we know if the average anxiety level here is greater than the average anxiety level here? Yes or no? Will we know if we test for that? If that is bigger than this, then the drug is effective. Again, the purpose of statistics is not to simply say this is bigger than that. Rather, whatever effect you observe has to or we're testing to see if it is significant or not. Good. If you do the study with 16 participants, this ends up being significantly greater than what you started with. You have an awful drug, correct? Your anxiety level peaked, but that is not the objective of this drug. It's supposed to bring it down. Good. So we're going to use the difference. Say, if you want to see the consistency between those two trials, we want the measures to be close to each other. In other words, I want the difference to be 0. Good. So the key word here is difference. And we're not going to look at a single difference, rather we are going to look at the difference in averages or mean difference. Good. So our procedure is going to be dependent on the mean difference. We will do an example next